Hello everyone, this is Tanmay Deshpande. My registration number is 19BPS 1057. So I am here to discuss about my project NAND2TETRIS. So the project NAND2TETRIS is basically the project in which we get to build our own personal computer which has several projects. It has around 13, 14 different projects which will eventually lead up and we'll be able to build our own personal computer. But the task given to us is to complete the first two projects. The first two projects of this course will deal with Boolean logic and Boolean arithmetic. So to start with, we'll be using a hardware simulator. Just one here, which is Windows batch file. Okay. So this should be our hardware simulator, in which this will be used to load a chip, and then this will, I will just start with loading the first chip. The first chip I will show you is the AND gate. So AND gate, so basically, I will just give you an overview of the simulator. So this over here, input pins, shows the number of input pins the gate has. This over here, HDL, this HDL deal is hardware description language. It is a language which basically deals with electronic components and mostly digital logic. So over here, we need to insert in the parts code, we need to insert the code, which is basically the logic behind the gate. So here it shows chip AND, which is the name of the chip. In gives the two input pins, out represents the output of a pin, which is only, we'll have only one output for this gate. And the parts code, we'll be using two NAND gates. Okay, so now let me just load the script and use the, okay, let's run it. So as you can see, the output values change with corresponding input values. Let me check my output. It shows a truth table in which evaluates to like 0 to 0 and 0 0. Since it's an AND gate, 0 and 1 corresponds to 0, 1 and 0 to 0. AND gate only gives a positive output, that is 1, when both the pins are same, that is high, 1 and 1. Let's compare it with the test case. Compare it. You see there are no changes, so this means that our code is correct. Let's move on to the next code. Next code is AND 16. So basically AND 16 takes in two inputs, but each input is 16-bit long. Okay, so we'll be using around 16 AND gates to solve this thing. Let's load AND 16, run it. It shows comparison ended successfully. Now let's check the output. So see, as I mentioned, it has 16 bits. Like each input has 16 bits. Okay, now let's test compare. You can see there are no changes. Let's go to the next code. Okay, let's go to the OR gate. The OR gate is a simple gate which includes two inputs and gives the output, which is either 1 or 0. OR gate gives the output 0 when both are 0, or else it will give 1. So we have used 3 NAND gates to get the corresponding output. Let this OR rate. PS3 run. Okay, comparison ended successfully. Check our output. Let's check our compare. Okay, so we see there are no changes. So it's a simple OR gate. 1 and 1 gives 1, and it only gives 0 when both the inputs are low. That's 0. Let's go to next one. OR 8-way. So OR 8-way takes 8-bit input and it will give 0 when all the 8 bits are 0. Otherwise it will give 1 all the time. Let's load this test script. Let's run. Output. See, all the 8 bits are 0. You can see over here. That's why the output is 0. Else everywhere there's at least one 1 in the input, and hence it shows the output 1. Let's go to the next gate. OR 16. So OR 16 takes 2 inputs, but both the input has 16-bit length. So it's a 16-bit number, you can say 16-bit input, but it has 2 inputs. Let me load the test thing. Let me just increase the speed as it's taking too long to execute, and then run. Okay. Okay. Let's check our output. See, you can see the output, and we can compare it with the compare step. You can see there are no changes. This means that our code is correct. By the way, we have used 16 OR gates to form this gate. Basically, it compares each bit one by one. 0 to 0, this 0, 0 and 1. So that corresponds to 1. So this corresponds to, this goes on and it compares each and every bit one by one. Let's go to next gate. Next gate is XOR gate. The XOR gate gives 0 when both the inputs are the same. Suppose both the inputs are 0, it will give 0. Else if both the inputs are 1, it will give 0. It only gives high output, that's 1, when either both the inputs are 1 and 0. Let's load the test script. So run it. Check the output. See, 0 and 0 gives 0, 0 and 1 gives 1, 1 and 0 gives 1, and 1 and 1 gives 0. Let's check out. Okay, so there are no changes. This means it's working perfectly fine. Let's go. Okay, the NOT gate. Simple NOT. So basically a NOT gate is just an inverter. Whatever you give an input, it will just invert and give the output. Suppose this is 0, it's showing the value 1. Suppose if I give 1 over here and try and execute, you see the change, it's 0. This is very simple NOT gate, and we are using NAND gate to get the result. Let's go to the NOT 16. Okay, so NOT 16 is a NOT gate which has 16 bits in it. So basically, okay, let me just load the test. NOT 16 and run. See, so NOT 16 basically for each bit it acts as a NOT gate. So if you see 0 over here, if you invert 0, you'll get 1. Same for the other 15 bits. See, let's check this over here. The least significant bit. here is 0. If we invert 0, you should get 1. Same goes on for the other bits. So now let's go to the multiplexer. So okay, multiplexer is very interesting. So multiplexer is basically, it has 3 inputs. Third is the selection input. The selection input works like, if the selection line has 0, it will give A as the output, and if it is 1, then it will give B as the output. No matter what's there in A or B, it will just choose what's there in A or B. It just depends upon the value which is there in the selection line. Now let me load the mux this file, run it. Output. See, you can see here, since there are 3 inputs, you will have around 8 test cases. Okay, see over here, selection line is 0, hence it should give the value of A. Value of A is 0, it's giving 0. The selection input is 1, hence it should give B. B's value is 0, therefore 0. Okay. And let's go to 4-way 16. Okay, so mux 4-way 16 takes 4 inputs. Okay, 5 inputs, in which 4 of them are each 16-bit long, and since there are 4, 2 raised to power 2 is 4. That's why the length of the selection line should be 2-bit long. Either the input should be 0, 0, 0, 1, 1, 0, or 1, 1. Okay, so let me load the test script and run. Okay. I guess the output isn't visible over here. Let me just load it in Notepad. See here. Okay, let me just compare it. Here, you can see the output and the compare file both are same. This means that we are correct. Okay. Now let's go to the next step. Next step is mux 8-way 16. So, alright, so mux 8-way 16 has 9 inputs, out of which 8 inputs are 16-bit long, and since 2 power 3 is 8, the selection line will have 3-bit long input, which can vary from 0, 0, 0, 1, 0, 0, 0, 0 to 1, 1, 1, 1. Load and let's check. Let's check our output. Oh, even the output isn't visible here. It will take time for me to go and show you the notepad, but I guess you have got a good idea by looking at the inputs. Okay, so now let's go to the next gate. Next gate is mux 16. Okay, mux 16 is just like a simple mux, but it just has, each input is 16-bit long. Let me just load mux 16 and okay, so we have used 16 multiplexers to form this mux 16. Let's check our output. Yeah. Okay, this is output, and let's just compare it. See, there are no differences. This means a project. So what is the code we have put in here is correct. Now let's move on to demultiplexers. Demultiplexers are basically just the opposite of multiplexers. Demultiplexer will give an output input comma 0 if the selection line is equal to 0, or if it is 1 it will give the output 0 comma n. Let me load the test file. Upload. Alright, let's see. The selection line is 0, so hence it should give output as in comma 0. So a comma b is in comma 0, so hence since in is 0, a is 0 and b is as usual 0. Selection line output input is 1, so this means that the output should be in the form 0 comma in. So in is 0, a is as usual 0 and b is 0 because in is 0. See, this selection is 0. This means the output should be in the form input comma 0. Now let's check the input. Input is 1, hence the value in a is 1 and b is 0. Okay, so now let's move on to the next step. Next step is debug's 4-way 16. So this is also similar, but just it has two selection. The length on selection bit is 2, so hence it will have 0 1 and 1 0 as. Let's run it. Okay, so here you can see the my output, and here you can compare it. There are no changes. This means we are going all right, we are all fine. Let's go to the Mux 8-way. So basically the Mux 4-way and the Mux 8-way are the same, just that the length of the selection bit is changing. Since Mux 4 this is Mux 8-way, this means 2 raised to power 3 is equal to 8, hence the length of the selection line would be 3. That means it will take 3-bit input, like 0 from 0 0 0 to 1 1 1. It will keep on changing. So we will have total 16 conditions over here, since the total value is 3 plus 1 4, 2 power 4 is 16, so 16 different combinations. Let's check the test file. Okay, so we don't see any changes, this means we are fine. By looking at this, I think we have come at the end of project 1. So now let's go to the project 2. So project 2 is Boolean arithmetic. And okay, let's see what. Okay, so the first thing I will show you in the project 2 is the half adder. So it takes in 2 inputs and has 2 outputs, which are sum and carry. So it is used to basically find the sum of 2 single bit numbers. So we will be using XOR gate and AND gate to perform. See, since I told you it is used to check the sum of the inputs. 0 and 0 correspond to 0. The sum is 0 and the carry bit is 0. 0 and 1. Sum is 1, but there is no carry bit, so therefore 0. 1 and 0. The sum is 1. There is no carry, therefore 0. whereas 1 and 1. If you do 1 and 1, you will get sum as 0 and carry as 1. This is simple half adder. Now let's move on to full adder. Okay, so full adder is basically just has one more input, which is C, which is the carry input. Which this is the There's one drawback in half adder, that it does not consider the carry if you want to add more numbers. So the full adder includes this carry as well. Let me load the test script. Okay, it has two outputs, which are sum and carry, similar to half adder. Yeah, and we have made this using two half adders and an OR gate. Let's check the output. So the sum corresponds to the sum of A, B, and C, and the carry corresponds to will show if there is any carry. Suppose here, okay, 1 and 1 and 1. If you do the sum of 1 and 1, you will get 0, and plus 1 will get sum as 1. But you have one carry already, which will be carried over as the output over here, and you'll get 1. Okay, so now let's go to add 16. Add 16 is basically, it takes two inputs, each 16-bit long, and gives one output which is 16-bit long. Let me load the script and output. So okay, so what add 16 actually does is, suppose you see this over here, 1, the 1 over here, and B 0 over here. It will just add 1 and 0. The output is 1. If you add 1 and 0, you'll get 1. So similarly, it just adds each bit by the corresponding bit of the other input. Made it using 16 full adders. Now let's go to the increment thing. Increment gate, it's just very simple. Increment gate is just used to add 1 to the corresponding input. Whatever number we have, we'll just add plus 1 to it, and then we'll get the output. Yeah, see. Okay, all 16 zeros over here. Increment does what increment does is just adds plus 1. We'll add 1 to the least significant bit. So we'll add 1 over here. 1 plus 0 will give you 1. So hence the output is 15 zeros followed by 1. Okay, now let's check this. It's all 16 ones. If you add 1 to the least significant bit over here, 1 plus 1 will give you 0, followed by 1, carry 1. So if you add 1 and 1, you'll get 0, and again you will get 1 carry. If you keep on adding, you'll get all 16 zeros, but you will be left with 1 carry over here, which is not to be counted since it has only 16-bit output. Okay, now let's move on to the final experiment, which is ALU. So this is the most difficult and most important part. So ALU does all the arithmetical operations. ALU stands for arithmetical logical unit, so hence the name. So ALU does all the complex arithmetics. Let me just load the script. Continue. You can see it has multiple various combinations: x and y, x plus y, x minus y, x into y, just all the possible combinations you can think of. So yeah, you can see comparison ended successfully. Let's go and check the output. Okay, so since the output is quite big, then so many combinations, we won't be able to see it over here. But and we even wouldn't be able to see if the output is correct with and compare it with the test thing, because there are way too many numbers and we can't even make out if the single bit change. And so yeah, that's it for the video. I guess I've covered all the possible gates and chips in the first and the second project. Hope you love the video. Thank you.